All right, good afternoon for Calc 2 here. So we're going to work on integration by parts again today, and we got some inverse trig functions and all sorts of fun things over there. So let's go to sharing the screen and get started with all of that. All right, so just wrong one. What do I want? How about this? All right. So here's the idea. We're going to evaluate, right? We've got cosine inverse. Okay, and how do we deal with that? Well, the inverse trig functions are actually very similar to the logarithm problem. Okay, we don't know how to take the integral of this thing. That's why they're asking us. Okay, just like we didn't know how to take the. Oops, let's go with one smaller. We only knew, right? We couldn't do with the logarithm there. We had to set it up as an integration by parts. Well, it's the same idea with inverse trig functions. Okay, so we're going to let we have a dv. Okay, so we can take the derivative of inverse cosine. That's fine. And then what do we have left over? It's just x, right? This is just dx. So we take our derivative here. That is -1 over 1 minus x squared. All right, and v is just going to be x. Okay, so the important thing with the inverse trig is we're going to take the derivative of it because that's a much easier problem. You guys know that, but the integral is not as easy. Okay, so let's go ahead and set this thing up. So this is going to be, right, this is going to be uv. So here we go, uv. So that's x cosine inverse x, right, minus v times du. Right? And negative times negative, we get a positive. There's a dx in here. All right, so we end up with x cosine inverse x plus, right, integral of x over square root 1 minus x squared dx. This is not so bad of a problem, right? This is a u substitution problem, right? We did this in the last chapter. So we could do something here, and you don't have to use u all the time. Okay, you could use a different letter, but let's let t equal 1 minus x squared. dt is equal to 2x. There's a negative, but I have an x. All right, so all I have to do, right, is put a -2 here and a -1/2 there. These will cancel. Negative times negative will be a positive. All right, so here is my, right, dt. Right, so this -2x dx here, that's going to get substituted for my dt, and I'm going to have t on the bottom, so that's going to be, right, t to the -1/2. So my answer here, right, is x cosine inverse x. Okay, and then we've got this deal, right? So this is eventually going to be a -1/2 integral. Now, what do we have here? We have t to the -1/2. That's what 1 over the square root looks like, right? And then we just have dt. So we go ahead and add 1. All right. So we have x cosine inverse x. Right, we're going to go ahead and add 1, so we have a -1/2 here, and then we have t to the -1/2 plus +1, right, plus +2, so we get a 2 over 1 divided by a 1/2. All right, do the 1/2s cancel? Absolutely they do. So this is equal to x cosine inverse x, and then what the heck was t? T was, right, t was minus, and we have, well, it looks like we just have the square root of 1 minus x squared, right, and then plus c. That is our integral, okay, of inverse cosine. Okay, so it's really important, right? You have to remember what the derivatives of inverse cosine were. That was -1 over square root 1 minus x squared. We almost never use this one because the derivative of inverse sine is positive 1 over 1 minus x squared. Okay, so if you had an inverse, if you had a slightly different value here, that would be fine to do that. But it would work out the same. It's just that maybe your sign, SIGN signs to get there would be a little different. And then the derivative of the tangent inverse, right, is 1 over 1 plus x squared. Okay, so it's important to remember your inverse. I know your book has inverse secant, inverse cosecant, and inverse cotangent. I will not ask you any of those probably ever. Okay, so that's not, those are not functions. Doing the derivative of inverse secant isn't something that has saved me at any particular time. So your chances of needing that off the cuff are slim, whereas this one happens all the time. So you might want to know, this one I would definitely memorize, and I would make an effort to make sure that this one was memorized. This one, as long as you remember it's the opposite of sine, you're going to be okay. But this one's really important. Not quite as much, but still important. Okay, but that's how you do that problem. Okay, so let's see here. Let's see. We did this one yesterday. We did. Did we do this one yet? Yeah, I think we did. I think we did that one yesterday. No, we didn't. But okay, not too bad though. I know we definitely did a sine theta. E to the theta kind of a problem. These are a pain. Okay. 8 is a pain as well. But we'll take a look at this one because this is an important one to be able to do. By the way, this one is too, like I said, this is a rite of passage. Everybody who's ever taken Calc 2 has done this problem on an exam at some point. Okay, so just fair warning on that. Okay, so here we go. We have integral of, I'm not going to use z. I'm just going to go back to x's, and that way, you know, we can change when we need to. So we have 3x cubed e to the x dx, right? That's a faithful translation of this problem here. Okay. So this belongs to a class of functions. Okay, usually in statistics we have an x to the n e to the negative x. So there's a little bit difference in mind for usually what I usually see, but this is a very standard class of function to integrate in statistics. So you're going to see this in your engineering classes when you talk about risk engineering a lot of times. So how do we do this? Okay, first off, we move the 9 to the outside. So 9 integral x cubed e to the x dx. All right, so let you pick which one you want, right? But the one you want to pick is going to get smaller, or the one that you can take the derivative of, right? The last problem, like dv, if I set that to be there, the inverse cosine, I'm like, well, there wouldn't be an integration by parts problem. We'd be done. Okay, so that's just going to be e to the x. This one is going to be x cubed, right? And then du, right, is 3x squared, and v is just e to the x. It's very nice they did this one to us to minimize how much stuff was going to go on here. So let's see here. To do our integration, right, we have the box. We have x cubed e to the x minus 3x squared e to the x. Okay, so we have 9. All right, and we have x to the 3 e to the x minus integral 3x squared e to the x dx. Well, this is an improvement. I got 2 instead of 3, but I'm going to have to do this again. All right, so I'm going to have to go ahead and take this little version here and push it down. So we have 3 integral x squared e to the x. All right, dx. And then what we're going to say is I've got an exponential times an exponent. Delightful. So what do we do with that? Well, we do integration by parts again. So we're going to say let u equal x squared dv is equal to e to the x, du 2x, v is equal to e to the x. So this piece here, right, this piece here is equal to 3 uv x squared e to the x minus integral 2, right, x e to the x dx. At which point you get to this and you say, oh joy, this is a polynomial times an exponential. Guess what we get to do again? We have minus 2, and then we're going to go ahead and have integral, right, of x e to the x dx, and say that this is equal to, let u equal to x du is equal to 1, dv is equal to e to the x, v is equal to e to the x. Okay, this is almost as fun as the problem we did yesterday. I mean, not quite so much fun, but close. All right. So here's our 2, and then our integral here is uv, right? uv. So it's x e to the x minus integral v du. Finally, an integral that I like. Okay. So this is minus 2 x e to the x minus e to the x. So this thing fit into a bigger piece, which was 3 x squared e to the x, right? So this is going to be 3x squared e to the x minus 2x e to the x plus 2 e to the x. Oh, I'm sorry, 3 times 2. That's not a 3 there. That's a 6. Because 3 times 2 would be 6. Do I have to keep rolling this up? Oh, I sure do. That's this part right was there. So we have to roll this up into here, and we have minus all of that, right? Because that's where this negative sign is. So that's where that negative sign is. And then we have x to the 3 e to the x. And this is all multiplied out by 9. All right. Ugh. All right, so we have 9x3 e to the x minus 27 x squared e to the x minus 56 x e to the x plus 56, or 54 rather, 54 times 6, 54 e to the x plus c. How much fun was that? More fun than anybody should be allowed to have, right? All right, there is a bit of a shortcut, all right, and this is called tabular integration. I usually don't like for students to do this, but if I throw you a problem like this, right, like this first, not this one. If I throw you a problem where this is happening, you'd be a fool not to use this. Okay, it's called tabular integration. So going back to our first value here, right? We have integral of 9 x to the 3 e to the x dx. So we're still going to call it. Okay, the reason why I don't like to show you this is because a lot of students will do this and just assume that it always works this way. I mean, there's never anything to look out for, and everything works just perfect. And that is not the case. So this is a special case, all right? Unless you learn all the exceptions and where to stop and all of that stuff. I would recommend stick with integration by parts as written. If you've done enough of them that you have a good basis for it, you could start moving on to some of these other shortcuts. You know, I'd hate to see you in the middle of statics. I'd hate to see you in the middle of mechanics. You know, oh, integration by parts, or worse, you have me for DE. You know, oh, integration by parts, I can't remember how to do it. I'm like, yeah, that's not going to work out well. So we set up the derivatives and the integrals, and we have x to the 3 and e to the x. And then we start taking derivatives. So that's 3x squared, 6x, 6, and 0. This is where you stop. Once you get to a 0, you stop. And the integral, well, I know it's been a long day, but I think I could manage to integrate e to the x multiple times. Okay, So the last thing we have to do is we have to put in our signs, SIGN signs. So plus, minus, plus, minus, plus. Okay, so the way this is going to work is that you take this value in the diagonal. All right, that's how we do that. So this is going to be, there's a 9 out in front, right? So we have x to the 3, e to the x, minus, right, minus 3x squared e to the x, plus 6x e to the x, minus 6 e to the x, plus c. And then we can just multiply this 9 through and then be done with it. So we'd have 9x cubed e to the x minus 27x squared e to the x minus 54x e to the x. I feel like I've messed up a sign here. I think that's better. And then minus 54 e to the x plus c. And that should be the same piece I got over here somewhere. Maybe a sign is off here. I think a sign is off. All right. We'll chase this SIGN down here. I think this negative, no. Oh, there's a negative out in front here, isn't there? So some of these are going to be off. Okay. So we're going to have to be careful about that. All right. So to worry about that, make sure you carry all your signs around, SIGN signs, SINEs too, if that's the kind of problem it is. But this is a very easy way to integrate an x to the n, e to the x kind of a thing, and that's where you want to use this. Okay, this technique actually does work for a couple of other things, but like I said, sometimes there's rules you have to remember, and it's a little bit more complicated. So tabular integration, next section we get the improper integrals. You'll see why. Okay, but for these, I don't like to give you problems where you have to do this multiple times. I figure if you could show me integration by parts twice, you could do it 100 times if you had to. And you're going to have to do it twice because there's going to be an e to the x sine x in there somewhere. Okay, so I don't like to ask, I don't like to ask these so much. All right, what else are we working on? We just did that one. We just did this one. Okay. This is another one where, well, evaluate the integral from 1 to 7, w squared natural log w. Okay. So yay, we're in definite integrals now. And what are we in? We're in w squared natural log w. Okay. So let u, right? And then we have a dv. Well, which of these can we integrate? Which one can we take the derivative of? Take the derivative of this one. So ln w here. dv is whatever's left over. All right. du 1 over, excuse me. Okay. d, we got to integrate this, right? We got to integrate w squared. It's going to be 1/3 w cubed. Right? And then we have our box. We're good. We can do this. We can do this. Notice that this was an exception. We didn't want to do the tabular integration on this one because we don't have to take this thing all the way down to 0, and I can't integrate this thing anyway. Right? If I tried this one, right, this is really w to the negative 1. If I take the derivative, we're going to be here for a while until we get to 0, aren't we? So you want to be really careful about, you know, what you're doing with all of that. Okay, so be careful about setting up tabular integration when you don't really have the right, kind of format to do that in. Okay, so here we have, right, here's our integral. We have 1/3 let's go with w cubed ln w, right? That's here. And then minus integral 1/3. And here we have, right, we have w cubed times 1 over w, dw. All right, so let's go ahead and make a little bit of room. So we have 1/3 w cubed ln w minus, well, we have 1/3, right? Do we have a third? We do. We have 1/3 integral, and I have w cubed over w squared dw. All right, so this is equal to, we have 1/3 w cubed ln w minus, and then we have 1/3 w cubed over 3 plus c. All right, so here we go. We have 1/3 w to the 3 ln w minus 1/9 w cubed plus c, and we're good. Okay, that's all we have to do with that. All right, it's good. So even though that one looked like it was going to be unpleasant, that turned out to be pretty straightforward, right? We only had to do integration by parts once. I know you're distraught. Oh, we're not done yet. We didn't have a plus c. We had a 1 to 7. Okay, we had a 1 to 7. So I'm going to pull out a, well, I'm not. I'm just going to go through and let it happen. Okay. So here's 1/3. Oops. I want this way to happen. Okay, so this was 1/3. Okay, we had a 7 cubed ln 7 minus 1/9. 7 to the 3. This was w evaluated at 7, right? Then we also had 1/3 1 cubed ln 1 minus 1/9 cubed, and this was w evaluated at 1. All right. Well, the natural log 1, that's an easy one. Natural log of 1 is 0. All right, so we can just make sure that goes away because the natural log of 1 is 0. All right. And we just have minus a minus 1/9 here. All right. And now we have a little bit more arithmetic to work on. There's 7 cubed. What the heck is 7 cubed? 49 times 7? $343. Oh, excuse me. I'm so sorry. I'm going to be yawning my way through your lesson here. Okay, so this was 1/3, 343 over 3, natural log of 7, minus 1/9 times 343, plus a 9th. I'm sure you guys can put that in a calculator and evaluate, okay, and then work it from there. Okay, so that is not too bad of a problem there. Okay. All right. So t squared sine 2t. Let's try that one. Actually, how many more do we have here? All right. Oh, we should do 14. We should do 14. Here's why we should do 14. Okay, so this is integral square root pi over 2, square root of pi. Okay, we have 3 theta cubed cosine theta squared, d theta. There's a class of integrals that we do not have closed forms for. Okay, we can't integrate them the way that they sit. Okay. And cosine of x squared, sine of x squared. Like if I just handed you that, you can't integrate that, okay? E to the x squared or e to the negative x squared. Like you can't integrate that. So there's certain forms that just don't work out so well, okay? So that's what I'm looking at for that one first. For this problem, they give us a little bit of a hint, right? They say make a substitution, then use integration by parts to evaluate the integral. Okay, so what we're going to do here is we are going to make a substitution here first in order to deal with this part here. Okay, so they gave us a hint. They said make a substitution. Okay. So why don't we say something like this? Why don't we do what letter do you like? We have, so I'm going to save U and V for the integration by parts part. So pick a different letter. Okay. How about we let T equals theta squared? And every time you make a substitution in calculus, you'll always take its derivative. Okay. So let's see what happens here. Okay. So what I'm going to do here is I'm going to say this is 3 theta squared times cosine of theta squared times 2 theta d theta, okay? Because I introduced a 2 here, I'm going to go ahead and put a 1/2 out in front. Those cancel, all right? And I know that t is equal to theta squared. Can I rewrite this in terms of t's and dt's rather than in thetas? I think we can. So what we're going to have here is we're going to have 1/2. I have a 3t cosine t and 2 theta dt. All right. Now we have integration limits. Okay. So if t is equal to theta squared, right? If theta is equal to the square root of pi over 2, what's theta squared equal to? No more square roots, just pi over 2. If theta is equal to the square root of theta, if they were the square root of pi, right, square root of pi here, then theta squared, right, is equal to pi, and that's equal to t. So our integral is going to turn into, right, we have pi over 2 here to pi. All right, so now we can just do integration by parts, right? Which way? So we're going to say let u equal 3t, du is just 3, right? dv is equal to cosine t, right? And v, what's the integral of cosine? I think that's sine. Derivative of sine will be cosine, so that's how that works. And then we can just do our box, right? So we have this integral is, put the 1/2 out in front here, right? And we have, what do we have? We have 3t sine t minus integral, 3 sine t. All right, so we're getting close. Oh, what's our integral values at? It looks like it was between pi over 2 and pi. All right, and then there we go. There we go. So this is just regular, you know, nice integral now. 1/2 3t sine t minus, what's the integral of sine there? Right? If I take the derivative of cosine, I get negative. So 3 cosine t, right? And we're going from pi over 2. You just plug those guys in, and plug this one in, and we'll be fine. Okay, so it's 1/2 3 pi sine pi plus 3 cosine pi minus 3 pi over 2 sine pi over 2, right? Minus. All right, there we go. So we can evaluate this. It's sine pi. What is sine pi? 0. We have 1/2 0 -1. Yeah. Minus sine of pi over 2. That's 1, right? So this is 3 pi over 2. Okay. Minus, and then cosine of pi over 2 is just going to be 0. Right? I'm looking at this like I should have a negative sign somewhere in here to be on the negative side. But, all right, that being said, okay, again, watch your SIGN signs. Okay, I'm a little careless with mine right now. But that is how we go ahead and do integration by parts for this. Okay, make the substitution first. Nice, they gave us a little hint. Thank you. And then we can go on from there. Okay. Here, make a substitution first, then use integration by parts. Okay. So we have integral x ln 1 plus x dx. All right, this was one of those substitutions that takes a little bit. It's a little tricky. I mean, in this case, it's supposed to be a little obvious, but it is a little tricky. T 1 plus x, okay, dt dx. But then we're going to say that x is equal to t minus 1. Right. So when I pull my integral here with a substitution, we've got t minus 1, right, times natural log of t dt. All right. Now when I pull my u and my v, right, derivative of ln t du 1 over t dv t minus 1, and then we got to integrate this. So this is going to be v is 1/2 t squared minus t. Yeah, integrate. All right, so here we go, integrating. It's uv, so this is 1/2 t squared minus t times ln t minus integral, right, t minus 1 over t dt. I'm going to change this up a little bit. Okay, so this is 1/2 minus integral. That's 1 minus 1 over t, isn't it? So 1/2 t squared minus t ln t minus, then we got to integrate this piece, right? That's just going to be t, right? It's going to be positive. What is the integral of 1 over t? ln t. Okay, we can't escape it. Okay, and then finally, yeah, that's it. There we go. Oh, plus, let's see. All right, and that's our solution. All right. All right, so what else are we doing this week? We are doing what's coming up here. Trigonometric integrals tomorrow. Trig substitution, partial fraction, okay. Oof, okay. So we'll do trig substitutions, or trigonometric integrals tomorrow. Trig substitutions and partial fractions will be next week. Maybe we could work on trig substitutions again at the end of this week. This isn't too terrible. This I always thought was kind of fun. But let's have a look. Oh, this is awful. Okay. Oh, that's one thing I wanted to talk to you about. LIATE. Okay. So this calls for logs, inverse, algebraic, trig, exponent. Right? So when you are picking like what to take the derivative of, okay, the order you kind of want to go in is this guy right here. Okay, so if I'm going to pick my u, pick the log first or pick the inverse trig function first. Okay, when they say inverse, they mean inverse trig function. Algebraic, usually want to, this will work. Okay. And an exponent and trig you don't usually want to do. This is not a rule. Okay, this is a guideline. There are problems where if you follow this, it will be the wrong answer or the wrong. You won't know it's the wrong answer until you're about 20 minutes through it. Okay, it's not that it's wrong. It's just it is not going to lead you to an answer. Okay, it's going to lead you to a dead end. So don't blindly trust in this and say, but this acronym said, I'm like, that is not what we are saying. We are saying that if you don't know what to pick for your U, these are the best choices to make if you got no other ideas. All right. But blind obedience is not allowed. So if it doesn't work out, you gotta swap. All right. So be careful about that. You're going to see this, and people are going to swear by it. It doesn't. It's a guideline. It's not a rule. Okay. It's a guideline, not a rule. So be careful about this. Okay. Same thing with tabular integration, right? It's too easy to think everything works with this shortcut. No, it does not. Okay. So I think we're good. Okay. I think that's what I wanted to show you for your pieces there. Yeah, that's a project. Okay. So yeah, I think yeah, I would not give you something like this on an exam and say memorize the reduction formula. That's not what we should be doing. Okay. But yeah, I think that's what I wanted to show you with integration by parts. We did tabular, we did this part, we did a couple of other pieces here. Okay, all the way at the top. First one we did was an inverse trig function. I will put this up on the YouTube so that you can follow along with it rather than rely on my crummy handwriting. But yeah, let's go ahead and close off integration by parts. And tomorrow we will start working on trig substitutions. Okay. So there we are. I'm going to go ahead and stop recording here, and we'll see what we're doing.